Welcome everybody to the afternoon of our workshop on networks of machine learning, for machine learning, and by machine learning. It's been a very lively and intellectually extremely fruitful set of exchanges. And this afternoon, we're very fortunate to have Aditya Akella from University of Texas at Austin and also Google talk to us. Like we have done for all the other speakers, we don't need to Google the speaker for you to rattle off the list of accomplishments. We really like to tell you, why Manya and I picked these speakers. And I think one of the things that's remarkable about Aditya is that, the things he's going to talk about today and the things he's been working on for several years were, I think, really well ahead of their time. The type of work that he's doing in really looking at distributed ML. When he started on this was, I wouldn't say fringe, but let's say, not mainstream. And now everybody and their sibling is trying to get in this. So, that's the sort of really visionary a type of research that's a pleasure to see. And today he's very generously sharing more of his vision with us. So thank you very much, Aditya, and the floor and screen are yours.
Yeah, thank you for the kind introduction and for giving me this opportunity. It's a great pleasure to be sharing with you some of the work that we've been doing in the space of network support for distributed machine learning. So basically, what I want to talk in over the next few minutes is essentially argue that we need to rethink the kind of network support we have today for supporting machine learning and training. In particular, I'm going to talk about two sets of things. One is how learning frameworks today interface with the network subsystem and how it is broken and how we might need to rethink it. And then I'm going to pop one level lower and start talking about the network transports that underlie these subsystems and why we might need to rethink it. And in both cases, what I'll do is I'll kind of highlight, the trends and the constraints and opportunities that is, essentially inducing this call to arms, if you will, for rethinking. And I'll describe where we fall short today and how we can overcome them by kind of applying simple design principles. So, if you look at ML training, it's getting more and more complex. It's not just compute intensive, as was the case with the first generation of CNNs and recursive neural nets, but it's also like extremely memory and network intensive today. Especially if you look at current generation of neural nets, such as the deep learning recommendation models and such that are used in large companies like Facebook, they tend to place a significant emphasis on a bunch of different resources. Right, so the models are getting very complex and extremely network hungry. So here's an example of sort of like the deep learning recommendation models that are deployed. Facebook uses something very similar. And also these things appear at Google and other such large companies as well. And so the training deployment, what's interesting here is that it's a mixture of different types of parallelism, especially data and model parallelism. And these different types of parallelisms tend to induce different communication patterns over the network. And these communication patterns, we'll also call them as collectives. Especially if you look at the bottom and the top layer multi-layer perceptrons or MLPs, these tend to be trained in a data parallel manner, meaning that these models are replicated across machines. And therefore, during training, they induce a collective called the all-reduce operation to essentially aggregate gradients. But if you look at the embedded tables that are shown in blue here, these are trained in a model parallel manner, meaning that these tables are sharded across different machines because these tables essentially hold sparse features and they're really huge and cannot fit in any one machine's memory. And so what happens during this feature interaction phase is that these embedded tables are essentially redistributed and they're joined with the bottom layer MLP to extract rich features that are then fed to the top layer MLP. And during this feature interaction, you end up inducing what is called an all-to-all collectives where all workers communicate with each other, right? So what's interesting is that this is not just sort of a deep learning recommendation model or a DLRM that's specific to Facebook. We are starting to see these kinds of complex models that are being trained at large companies, Facebook, Google, Amazon, what have you. And it's not just these sort of all reduce and all-to-all type of collectives that I exemplified on the previous slide, but also many other interesting collectives such as many-to-one, one-to-many, reduce, scatter, all gather, what have you. So all of these different collectives are essentially placing a significant emphasis today on communication efficiency during training, right? The other trend that is going alongside this growing complexity of models and the various interesting rich collectives that are emerging is that network infrastructure is also changing dramatically to support training. So, today we are, this is an example of the machine architecture at Facebook. Essentially what you see here is a 4-socket CPU with a 400 gigabit per second NICs. There are 8 GPUs with a fully connected NV switch fabric. And also each GPU has a dedicated 100 gigabit per second RDMA NIC. And within the machine, you see things like PCIe and NVLink, but also across machines, there's RDMA and Ethernet connectivity. So essentially what you have when you take this machine and connect it up to other machines across the network is the training infrastructure not only has very high throughput, but it also has significant path diversity with different communication channels and non-overlapping interconnect pathways. So what I'm going to argue in the first part of the talk is that in order to support really large-scale models training in the face of these emerging network technologies, we need to think about how we do training in sort of a system stack perspective in a systematic manner so as to unblock communications from progress of training, okay? Let me explain this by essentially delving into how ML stacks run today and how that might come into picture here. So here's a view of a modern distributed machine learning stack. At the very top, users define a model using something like PyTorch. This model is converted into a directed acyclic graph of tasks, and each task is parallelized across a set of devices. And here, I show 3 tasks in orange, A, B, and C. And here, these specific tasks are communication collectives like all-to-all and all-reduce. Now, once these collectives become ready and the DAG executes them and they're ready, they are essentially the ordering of how to execute these collectives is determined by the scheduler shown in the third gray box here. And typically, the collectives become ready in a first come, first serve manner. And the scheduler also sticks with this default FIFO style of executing these collectives. Okay. Based on this order, the scheduler then submits these collectives one at a time to the underlying communication library. And the communication library then decides the actual plan for executing a collective. So for example, it might take the all-reduce collective and it might use the nickel ring all-reduce algorithm to execute the collective. And then the communication layer submits the appropriate kernel to the GPUs, to a particular GPU stream to execute it, right? So this is kind of how pretty much all of distributed machine learning training works today. And there are multiple problems with this picture. The first thing is that this FIFO scheduling that happens in this gray box is very naive, and you can do a lot better than that. The second issue is that the scheduling choice happens way up and way early on during the planning. The third problem is that the API between the application layer and the communication layer is sort of all you can do is submit ready collectives one at a time and the underlying layer executes them. And essentially what is missing from this picture is visibility across the stack. If you look at the scheduling layer doesn't really have a sense of the overall cluster, what the network looks like, what multipath opportunities may be available, and how to systematically take those into account. And likewise, if you look at the bottom layer, the communication layer, that doesn't really have a global sense of what the overall the DAG looks like and where a particular communication collective may fit within the DAG and how to make reasonable, intelligent decisions about how to execute it. Okay, so the upshot of this design is that if you look at how communication happens today in distributed training, it ends up significantly bottlenecking the progress of training. So this picture actually shows a kind of a scaled version of how DLRM training execution trace looks like. And here the trainer creates 2 streams for every GPU, one stream for communication operations and the other for compute operations. Compute is shown on top and communication on the bottom. And this trace is basically showing the kernel execution events on these two streams as they happen. And essentially what we see is that as communication ops are scheduled and submitted in a FIFO order, and the COM layer is forced to deal with these large collectives that are submitted, there are significant communication delays, and these delays tend to block compute kernels from making progress, and they create gaps in the compute stream. So in this case, for example, you can see that the A2A embedded collective delays the backward embedded collective, and likewise A2A prep delays the forward embedded collective, and so on. Right? So the poor execution of the communication layer ends up creating significant gaps in the computation layer. They take the stack to make spot fixes to different points, right? So for example, there are some works that look at changing the scheduling order. So they kind of move some ready to run collectives around to earlier stages in the execution so that you can achieve better computation and communication overlap. And as this example shows, by moving those operations, you can improve the overall execution time of your training iteration. But in order to further reduce these gaps, the gap G1 and gap G3 here, what we might actually benefit from is topology-aware, network topology-aware execution planning, okay? So here what we are proposing is that we take these different collectives, the all-to-all and all-reduce and all the different collectives, but break them into smaller sub-collectives or patterns, which we're going to call motifs. Examples are shown at the bottom here. Each motif is basically a subgraph of the overall collective, both with a physical plan that indicates the specific subtopology that it is going to use, as well as the interconnect that it is going to use, right? So here I show an all-reduce collective that is broken into 2 types of motifs. There is one machine local all-reduce that's happening, and then that uses machine local NV switch interconnect, and then cross-machine collective that uses RDMA across the different machines. So you take one all-reduce collective that spans many processes, and you kind of divide them into these sub-motifs that can use different collectives. So what these motifs enable is that they enable better communication overlap with other communication that might be happening. So in this example, you can take the all-reduce and the all-to-all collectives, and you can use non-overlapping communication channels to execute these collectives as and when they become available. And so what you can do is you can, for example, allow all-to-all to start much earlier than it could when you are not doing this kind of collective splitting into motifs, right? So these motifs, as this example shows, are used today. So for example, this is done in Nickel, can allow the left-hand side optimizations today, but they're used in a very limited set of a manner. There are specific templates according to which these motifs are used. The second issue here today is that the collective reordering and motif style optimizations, these are viewed as independent optimizations. But you could do a lot better by combining these 2 things and doing joint optimizations across ordering and across these motif style packing of communication. So here, what we get with the joint optimization of both scheduling and rich execution planning, we get significant improvements because we enable not only computation overlap with communication, but also communication and communication overlap. So we are able to simultaneously maximize all possible overlaps that might be that might become evident during training, right? And what this ends up giving is, in comparison with standalone optimizations of reordering, scheduling, and execution planning, when we combine the 2 things, we end up further significantly improving the overall picture and reducing the gaps in the compute stream as much as possible, such that you can improve your per iteration completion times, and as a result, the overall training throughput. So the system we built called Syndicate is a new stack that essentially allows for this joint optimization between scheduling and collective execution planning. And the design of Syndicate is essentially motivated by software-defined networking, where there's a control plane and a data plane. So what Syndicate does is in the control plane, we do the joint optimization asynchronously without blocking any of the data plane optimization operations. This asynchronous joint optimization takes into account the current network topology and the available capacity, as well as the overall training DAG. It takes that as input, and then it conducts a probabilistic search over the space of all possible orderings and motif splittings that are possible to pick a candidate best plan that has the lowest cost. Okay, and then it takes this joint optimized plan and provides this as declarative instructions to the data plane. The data plane is largely dumb and it simply enforces these plans. So a lot of you will be reminded of the SDN style architecture from looking. There are two parts to it. The first is the execution plan, which basically shows how to break each large collective into smaller motifs, where each motif can execute over a specific network subtopology, for example, local NVLink versus remote RDMA or Ethernet, as well as prioritized annotations over those motifs that indicate the actual scheduling order that should be enforced in the data plane, right? And the scheduling order gives the order in which these motifs should be executed. Right? And then once this plan is provided, the bottom enforcer layer essentially enforces these plans as indicated by the priority order. Okay. So this is a sort of a whirlwind overview as to how we designed Syndicate and how we kind of took out the responsibilities that were baked into the scheduling layer and the execution layer today, pulled it out and essentially conducted joint optimization, allowing a better exploration of possible orderings and execution plans that can most effectively leverage the parallelism available within the network, enabling optimal overlap of computation and communication. So this we are going to open source Syndicate pretty soon, but this picture gives you an overview of the kind of benefits we see. Here we have we are running this in production at Facebook, and essentially what we are comparing here against is a state-of-the-art scheduler. This does intelligent scheduling of moving just the collectives around. But it doesn't do joint optimization. That's shown in blue. And the orange, which is hand optimized models, where the programmer independently decides how to take a large collective and break it down into small collectives and does a lot of homework manually to decide on how to break up the collectives. And essentially what this picture shows is our approach that automatically searches through the space of joint optimizations that are possible, results in significantly better performance measured here in throughput relative to both the state-of-the-art schedulers as well as these hand-optimized models. And another interesting observation from this is that we are able to do this while also improving the overall utilization of the compute resources and resulting in less compute idling. And this is despite the fact that we are able to substantially reduce the per iteration time. Even with the reduced per iteration time, we are able to very effectively use the limited amount of computation that is available. All right. So that's the first contribution. This is new work. We just submitted a paper on this topic. I'm happy to take further questions about this. And the main motivation there is let's take how learning jobs interact with the underlying communication fabric and see what best we can do with it. What I'm going to do is to switch gears and then look at the actual communication fabric here and start to motivate, some ideas. I won't spend as much time as in the first part, but some ideas on how we might need to rethink the transport layer protocols itself in that context. And the specific thing here is the potential for in-network acceleration that becomes available. And the need to rethink, the low-level transport and protocols emerges because the unique workloads that are induced by training can interact with sort of these advances in switching and network technologies, and that can play a huge role in how effectively you might be able to do training at scale. Right? So the specific technologies I am talking about are programmable switches and NICs, and these can be used to offload expensive learning-related tasks such as gradient aggregation and other such things, but also the communication that underlies moving gradients and aggregating them and so on. So the consequence of this is that you can free GPUs from running these kernels that correspond to these learning-related tasks, but also potentially free CPUs and GPUs from doing ML-related network processing. And finally, by offloading some of this computation into the network, you may actually be able to improve the overall communication footprint that you may induce. Okay. And what I'm going to argue here very quickly is that the reason there is a need to rethink the transport is that we want a new transport that takes the ML specific nature of the workloads into account, yet it is straightforward to design. But at the same time, because these accelerators and these NICs and switches are sort of part of the network infrastructure, we need to pay close attention to how such transports can help democratize the benefits of in-network acceleration in the sense that we want multiple tenants that are simultaneously running to be able to leverage these acceleration benefits. And this also means that we cannot assume that acceleration benefits or acceleration capabilities are always going to be available. We might need to, and we might encounter a situation where all of a sudden accelerator does not become available because of heavy contention, for example. Okay. So here's a quick example. So the toy example I'm going to play with is this parameter server style distributed training approach. Here, if you use legacy transports between the workers and the parameter server, such as TCP or ROCK-EA or RDMA, then the server can quickly become a bottleneck, communication bottleneck, but also the amount of computation at the server can quickly become a bottleneck. So the main idea we're going to start thinking about is how do we put a programmable switch that can do stateful computation to offload some amount of gradient aggregation into the switch. And that aggregation has the benefit of offloading some computation from the server, thereby enabling the server to become more scalable, but also reducing the communication between the switch and the server, and basically improving the communication bottlenecks that are there. And potentially, if you're careful, you can enable multiple jobs to share these programmable switch resources to achieve such scaling benefits at the server and also bandwidth scaling benefits. Okay. So one first cut way in which you can do this is to take the switch stateful computational resources, sort of statically partition it across different jobs, and then have a programming model that allows the jobs to offload gradient aggregation into these programmable substrates. But the static partition has obvious downsides, like it tends to be, it's not work conserving, it tends to waste resources, it cannot scale with multiple jobs. It also assumes that these statically allocated acceleration resources are always available, which, as I said earlier, might not be the case. So the system we designed called ATP is basically something that allows democratization of these switch level acceleration by playing with well understood classical notions from networking, such as soft state and best effort behavior. Right. So essentially, what we do in ATP is that in ATP, we dynamically allocate switch memory at a per packet level. The switch takes the overall programmable state that is available, and it takes a part of it and allocates that memory to be used by multiple concurrently running jobs. This memory, you can think of it as being organized as an array of aggregators. Each aggregator is accessed by an index. And whenever a worker corresponding to a job is ready to send its gradients over to the parameter server, the worker hashes a chunk of that gradient to a particular aggregator. If the aggregator is free, that ends up being assigned to that worker. All subsequent workers' gradients, when they hash to the same aggregator's location, are aggregated in that location. And once the aggregation is complete, the aggregated chunk is sent over to the parameter server. Okay, so this happens on a per gradient chunk basis, and each gradient chunk maps to a particular packet. So, for example, all the blue gradient chunks corresponding to one gradient at the end of an iteration map to the blue aggregated region, and the green gradients chunks can map to the green aggregated region. At the end of this, when the parameter server pushes updated model parameters corresponding to that chunk back over to the workers, we essentially clear up that aggregator state from the switch. So in this sense, the switch aggregator state is basically soft state. It is ephemeral. It only lasts for roughly one round trip time, where the to be aggregated chunks are transmitted between the workers and the parameter server. So this is a very simple idea, but it allows us to opportunistically use aggregation state inside the switches as and when it becomes available, but also clear it up whenever we are done using it, making it available potentially for other jobs to use. So there are a bunch of questions that might arise, like, for example, some corner cases, like how do we handle packet loss, and how do we deallocate this state without involving external involvement? And we address that in our paper that I'm happy to share as well. So one thing that might happen, and this is something that I hinted at, is that this acceleration capability may not always be available due to heavy contention. And here, the basic approach we have is that of enabling best effort aggregation. So here, what happens is that whenever a worker hashes its gradient chunks to a particular aggregation location, and it sees that that location is being used by another job, say a blue job, the gradient is directly forwarded to the parameter server, and all subsequent workers' gradients are similarly also forwarded to the parameter server, and all the aggregation happens at the parameter server as opposed to inside the switch. So what this allows is for us to sort of seamlessly move aggregation between the switch and the parameter server, such that whenever there is contention, you offload you onload the parameter, the aggregation onto the parameter server, but when resources become available, you offload them back onto the switch again. Okay. So again, this is a quick view. This is open source. You can play with it today. And what this picture shows is that as we make things dynamic and as the amount of contention in the cluster becomes available, our performance difference in terms of how effectively we can support high throughput training becomes markedly better compared to statically allocating programmable switch resources. All right, so that's sort of a whirlwind tour into sort of like some directions we are exploring in the network support for distributed machine learning world. As Muriel hinted at the beginning of this talk, it's kind of become a cottage industry in recent times, but I still want to argue that it is early stages for this topic. We barely touched the surface in terms of rethinking the interfaces in the network stack, and in terms of somewhat changing how we view the underlying network transport in how it leverages in-network acceleration for machine learning. But there are a lot of other interesting directions that are worth pursuing at this intersection between machine learning and network support. For example, how might you leverage both NIC and switch-based acceleration? How might you integrate the syndicate style network substrate optimizations with existing cluster and network schedulers that are out there? And even sort of if you look at emerging directions in multi-terabit per second networks and microsecond scale round trip time fabrics, and you overlay machine learning workloads on top of that, what are the right transport protocols that we need to redesign to best use those fabrics to support such workloads? And how might we tune those to the specific attributes of machine learning algorithms? And sort of what should, for example, congestion control look like in this world? And also, sort of given how many bytes are essentially in the service of machine learning training workloads in clusters today, we might also want to ask, can we build ML-oriented network switches and ML-oriented designs, and what feature sets might such switches include? So I'm going to conclude this talk here. I think I'm a little over time. I'm happy to stay on for a bit and take questions, but I think this is a tremendous opportunity for a lot of fundamental work that we as a community can do to bring systematic thinking to this space and build core building blocks that others can leverage and build on top of. Again, thank you for giving me this opportunity. Happy to take questions.
Thank you. Thank you very much for a fantastic talk, Aditya. I don't see questions in the chat right now, but I wanted to ask you a question because very much your work seems to have, you hinted at this, a feeling of revisiting the stack, right? And in particular, what you're having are things that were traditionally user-space computation, very much separate from networking, really reaching into networking. And I think when we look at the evolution of networking right now, there's a lot of movement for particular transport to be moved up into user space itself, right? I mean, something like HTTP is officially in user space, but is really just a transport network. And, things like QUIC, I mean, they're really, it's become one of the biggest transport protocols. And it's really in user space. It just opens a UDP socket and off it goes. So do you see a convergence there that can be used as transport moves up into user space? Do you see a convergence, something that you can use?
That's actually a fantastic question. So yes, transport is moving into user space. But I think, especially in the machine learning context, the overhead of moving bits as they arrive from the network over PCIe into user space, processing them there, moving them back out may actually undermine the overall performance. So there is, at various companies, there is a push towards, trying to do as much as possible without ever entering user land. Mm-hmm. But there are some things for which the user space involvement is a fundamental necessity. For example, dealing with things like failures and just restarting computation and things of that kind. So the question that it is really boiling down to is, what is the right division of responsibility? If you think of the entire set of things that we need to do in the transport land, what must be done at the user layer, and what could then be accelerated as best as possible by the network layer, right? Or by the underlying substrate. And so this is sort of like a classical re-envisioning of the end-to-end principle, right? So like, what is that best common case engineering you can do within the network that gives the broadest set of benefits for everyone, while doing the most essential things that must be done in the application land out in the application land. So I think that principle is a good guiding principle to say, if I take the entire set of things that I'm trying to do in transport, here is a way of thinking about what should go in the user space and can be best done over there, versus what all can be done in an accelerated manner inside the network that matches best the performance expectations we have for machine learning.
Mm-hmm. Mm-hmm. Right. We have no, thank you. So it may be that transport ends up in the user space and computation ends up somewhere in the kernel. So what you're saying is they may flip where they hang out. Mm-hmm. There's a comment, question from Abdi Mashiri, I think, regarding whether this could be combined. I'm just going to interpret it broadly, whether this could be combined with security aspects.
I see. I think that I'm not making any changes to the security model except in the multi-tenant kind of setting, right? So the offload optimizations and collectives, those are all sort of single tenant, and they preserve whatever security model that exists in networks today. The things that leverage network acceleration, where you're leveraging a common hardware substrate, there you may need to have more principled thinking around things like security and potential side channels and issues of that kind. There is definitely a potential for security issues. There is some orthogonal work that we are doing that looks at how might we design these acceleration substrates with isolation primitives, both performance isolation primitives, but also being able to isolate data communication and memory accesses. But I'm happy to discuss offline about that. This talk per se just looks at performance and largely ignores security questions, but that's a important question, especially in the multi-tenant case.
Fantastic, thank you. So at this point, I wanted to thank you very much. I also want to thank all of the attendees for their participation and just for making this online workshop really work so well. I want to invite you all to join us tomorrow again, 11 a.m. Eastern, 8 a.m. Pacific Standard Time. Actually, I believe we will be starting at 10 minutes after the hour. I'm just verifying right now. So yes, we'll be starting at 8:10 a.m. Pacific, 11:10 a.m. Eastern. And we have a fantastic set of roster of speakers lined up. Pavan Balaji from Facebook, Brighton Godfrey from UIUC, and Ganesh Anantharayanan from Microsoft Research. So really very distinguished set of panelists again. So thank you all, and I look forward to seeing you, and particularly thanks to Aditya again.
Thank you so much.